point and Q is parallel to BC.
Interesting.
Don't know the proof.
Is it also collinear with? No, but it's parallel. Okay. All right. Let's see. Oh, it's already 11:04. VT, if we know VT is parallel to BC, then is that just Rimes' theorem? Oh, because C1QSK is cyclic. And VT is parallel to BC. I think that's Rimes' theorem, like Kahn is saying. Yeah, that's just Rimes' theorem. That's a good point. Because we have SK, and then we have BC, VT, and C1Q are like all parallel. Okay. I mean, so it seems like could we show that angle QGA is angle IGA? Yeah, I'm not sure how we do IGA. So we can kind of calculate the angle QI makes with BC, and yeah, I think if we keep working on this, we might spend like the rest of the time on this problem. It's up to you guys. It's a nice one though. But yeah, I think we got the main part showing that this is collinear. I think for the first video, I'm gonna like break this problem in half. So like everything we found so far, I'm gonna put in the first video, and then everything after that, put in the second one. So Q, I, and G. Oh, I think we might be able to use the radical axis theorem to finish it. So this circle, and what were the three circles I had in mind? And this one. So QI, we want to show, oh no, we want to show QI, MK, and ZH concur. If we can show UH, MK, if we can show that cyclic, then that would solve it. So yeah, this is my idea. I'll just type it up. First, show UHMK is cyclic. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . then by the radical axis theorem on UHMK, and then ZUQHT, oops.
Did you guys prove that TD and HK meets on E on the 9-point circle? And I just realized that it is very, very simple. You can just keep the original points and I'll just draw a new one. I'm gonna present to you.
So we
It's
proved
really
it.
short.
But you have another proof of it. Are there any points I have to?
It's really short. I think you should just draw a new one, and then just keep point K, T, D, S, and the triangle ABC, and then that's it.
Let me. I wonder if I can copy this whole thing because I don't want to delete this solution.
You can just open a new GeoGebra tab.
Yeah, that's what I'm going to do. All right. Oh man, why does it do that? I'm not sure if it'll let me copy it. No, it won't let me do it. Okay. I think I'll have to go to let's see if I can copy even just a portion of it. No, it won't let me. Okay. What if Con, you mind if I take it from my message to you?
Sorry, do you say anything to me?
Oh, tell you what, let me just draw the picture without the question. So basically,
I can read it for you. The tangent at BC meets at T.
Okay. All right.
And we draw the altitude AD
Right.
of triangle ABC. Also, let H be the orthocenter.
Okay. And then M and N are the midpoints, is that right? So what's after that?
You let AG meets BC and circle ABC.
Okay.
It meets BC at M and the circle at K.
Okay. All right.
So we need to prove that HK meets TD on the 9-point circle.
Yes. Okay. All right. So
Can you let HK meet TD?
yes. All right.
Okay, let's call that point I, like the previous one.
All right.
Okay, so first I'm gonna let HI meet the circle again at another point.
Okay.
Okay, so and HD meets circle at another point.
All right.
Yeah, and then yeah, it is the reflection. So I claim that we need to prove that I is the midpoint of HE, because
Yeah.
then a homotopy at H takes E to I.
Yes.
So it is the same as ID is parallel to H prime E.
Yes.
Or that is equivalent to TD is parallel to H prime E. So this is where I found this property. You need to draw the altitude from B to B and C to AC and AB.
Okay. I should change it so that it's not just like the Euler line. All right.
And then you label the intersections. Then you let FJ meets BC at a point. Let's call that point G anything. Yeah, let's call it L. Then we know that LDBC, the cross ratio LDBC is -1. So in other words, D lies on the polar of L with respect to O, and also T lies on the polar of L. So we know that TD is perpendicular to OL.
Okay. So TD is perpendicular to OL because so D lies on the polar of L since the cross ratio is 1, and D lies on the polar of T. So therefore TD is the polar of L, and so TD is perpendicular to OL, and okay, and then we want to show H prime E is perpendicular to OL. Okay.
Yeah, and H prime E is perpendicular to OL, which means I'm gonna put that LE equals LH prime.
Okay.
So this one is it's the same as saying that E lies on a circle with center L and radius LH. Can you draw it?
Yes.
And that is true because we have angle H prime EH is angle DAM, and it is angle LHLD, which is 1/2 of angle HLH prime. So we are done.
Okay. Okay. So this is a separate proof that IH and K are collinear.
And we did all those things, and now Khan just goes and crushes this part of the problem.
But the thing is, so yeah, the good news is that all the work we did might be worth it because we could show by the radical axis theorem, although there still might be a way to do that using this. So yeah, for the first part of the problem, yes, it could have just been this way. But then I think, what was Q? Q was the perpendicular from A to the Euler line. Is that what Q was? Sorry. No, I'm sorry. Q is the Q point. Okay, so let's see. So AH. Okay, so we want to show that Q, I, and G are collinear.
There's a fun fact that if you let can you label the intersection of Ti and E and FL? Ti and FL. You don't have to draw it because
it's already there.
It's already intersected.
All right.
Yeah, that point right there. Ti and FL.
Yeah.
It lies on HM. It
That's
is
the
easy
one.
proof.
We proved it.
Yeah, we proved it. Yeah, we proved that. Okay.
Oh yes. Yeah, that's it. Sorry.
That's all right. But yeah, thanks. And then showing QI and G are collinear. Let's see. So we know IH equals IE, right? And so LI is obviously perpendicular. I don't know if that would help. But yeah, basically, let me just go back to this for a second. So my idea was, and I think it might finish it off. Like once we show that these are cyclic, so this circle, and QI MKT. Or I could just say QIMK. That would mean that UH, MK, and QI. So UH, MK, and QI are concurrent. And then that would solve the problem. So yeah, can we show UH, MK as cyclic here? We don't even need V.
I'm sorry, but which one is cyclic?
So we want to show UH, MK is cyclic, and then that would solve the problem.
But just to say, we already know that H, M, K, and V is cyclic. We just need to show that U lies on that circle also.
Okay. Yeah, so HMKV is cyclic by Rimes' theorem.
No, that is something we proved before and doesn't.
Oh yeah, that
relate to
is
Rime.
that. Yeah, from this, right? Well, wait a sec. H. Yeah, just because this. Yeah, I remember you mentioning it. But yeah, it looks like just an angle chase because we just need to show that this equals that. So yeah, we would need to show U lies on this circle. Yeah, maybe that's trickier than it looks because U. Oh, U, Z, and V I think might be collinear. Let's see. Let me draw the line through U and Z. Well, maybe not actually. Yeah. So maybe it isn't really that easy. Yeah, it's harder than I thought it was. You want to go back to what Khan was doing? Let's see. So we want to show QI and G are collinear. I wonder if, so if we reflect H about Q, then I think we should be able to show it lies on this circle. And if we reflect H about G, it's that, yeah, that's the thing. This point doesn't look as special. So yeah, I think it's significant that these both lie on this circle. We just want to show G. So G is like, G is, so GH2, let's see. So this is like the, O it would be the midpoint of those two, right? Yeah. And I think it's a coincidence that it looks like it passed through F. So I don't think that's true in general. You guys want to try a different problem before we finish, or do you want to just keep going with this one?
Let's do another one. We have been doing this for way too long.
Yeah. All right. Sorry, I gotta move this out of the way to, all right. Oh, that one's a little tricky, I think, actually. Let's see. This one looks like it might be easier. So we have a triangle ABC with end center I, and we draw the circumcircle. center O. And then we draw the orthocenter BIC. So I think this is kind of like a well-known, like, I feel like I've seen it a lot of times before. And then okay. So that's H. And then T is a point. Okay, so T, basically, we just want to draw this circle. So it's like the Sharkey double point. And the circle AIO intersects IHX. And we want to show AX and HT intersect on the circle. Let's see. So I feel like there's a lot of problems with BIC, right? Or I'm sorry, with H. What are all the lemmas with the orthocenter of BIC? It's like,
for example, one lemma is that H lies on the Schwartz line of the orthic triangle. I mean, the in-touch triangle, DE and F.
okay. So the Schwartz line, I forget, how do you construct that? Is it like you take the midpoint of the altitude or something from F to DE?
Yeah, and also midpoint of DE, and those two are linear.
Okay. So first of all, TI first of all, we know this is perpendicular right here. And if you take the midpoint of this and the midpoint of DE, then those are collinear. I thought there was some other property though of H. Maybe not. So if you reflect H, okay, so
Also, but I don't think that this lemma is any useful in this problem.
is useful. Okay. I thought there was something like if you draw the point where BHC and something else is a parallelogram, then is that like the X center? I think there's something like with X centers. So like, I wonder if the point which makes this a parallelogram is the X center. Because I think that was the lemma. or if you draw the X center, so I'll do it using the in-center X center lemma. Let me shrink things a little bit. Then I think this is a parallelogram. Yeah, that was it. And is that easy to prove? Should just be an angle chase, I think.
Not even that, because we know both HC is perpendicular to AB and BIA is perpendicular to IB.
Okay.
So HC and BIA are parallel, which means it's a parallel cone.
Okay, so HC and BK have to be parallel for that reason. Yeah, because these are both right angles. So yeah, that's a parallelogram, and K is the X center. We want to show AX and HT intersect on the circle. And yeah, I want to make it so that it's like you can see that intersection point well. It's not that easy to do. Now it almost looks like HB. I don't want to make HB and AB look like the same thing. For this session on the next one. Yeah, definitely.
There is a session similar to this one, and I remember we didn't solve that, but then I solved it after the session.
Okay.
So the problem of the session, the session that I'm talking about, it is when you let the circle AIO meets ABC at a point.
1 sec. Okay.
Then we have HTIM is cyclic. That is the session.
Okay. We're HTI and M. And I wonder if LI and M are collinear? No, I don't think so. I wonder if MI is tangent to both circles.
Yeah, exactly. If we use this problem that HTIM is cyclic, then we are done.
Oh, really? How?
Yeah. Wait, let me just do a little angle chasing here.
Okay. Okay.
I think we should let L be the intersection of HT and ABC and circle omega.
Okay.
Then we let LA meets HI at X. Then we're gonna prove that it is cyclic.
Okay. So call that X prime. Sorry. Oops. What is going on here? Okay, let me call it X prime. Let HT intersect ABC at L. Let LA intersect IH at X prime. Okay.
Okay, so I'm gonna say what I'm gonna do here. We're gonna prove that X prime is the same as X, which implies X prime lies on the circle AIO. And by the lemma that I said we had on a previous session, we have AIOM is cyclic. I'm sorry, it's actually we define
HTIM.
M as HTIM. So we have angle AMI is angle I'm sorry, angle X prime IM is angle HTM is angle 180 minus angle LTM, which is 180 minus LAM, which is also X prime AM.
Okay. All right. So let me write this out. So okay, so we want to show that this is cyclic, but we know that this is cyclic. So by a previous problem on the channel, HTIM is cyclic. And then an angle chase proves that this is cyclic because okay, so we want to show this is cyclic. We want to show AIO X prime is cyclic. So okay, so did you show that angle X prime AI? So how do you show
X prime A is X prime AM.
Is X prime AM?
We have yeah.
Okay, so I'm gonna sorry, let me think about this. So that was X. Let LA. So we're letting LA intersect it at x prime. We want to show x prime lies on IH, right?
Well, I mean that we let LI meets IH as at x prime, and then we're gonna prove that x prime M is cyclic.
Okay. So x prime. So we want to show. Do you show that x prime AM is x prime IM? Is that how you prove it?
Yeah.
Okay. So x prime AM. So x prime IM equal to angle HIM, which is angle HTM. Which is let's see. Okay. And then x prime TM or x prime AM is 180 minus MAL. Okay, so LAM, which is 180 minus, okay, HTM, which is 180 minus LTM, which is 180 minus angle LAM, which, I'll break this up, 180 minus LAM, which is x prime AM. And that means that x prime AIM is cyclic. And that implies x prime equals x, which implies AX, HT, AX and HT intersect on omega. All right, so we probably have time for one more problem if it's an easy one. So let's see.
Actually, in the session we didn't prove that. I mean, we couldn't solve the problem that HTIM was cyclic.
So you
But,
proved it
yeah,
after
I
you
can prove
said-
it now.
Okay.
Yeah.
All right.
So should I write out a solution?
Okay.
Maybe just write it briefly.
Yeah. Just a bit the main ideas.
Oh, okay. So can you connect JM?
Yes.
And can you draw the line through I perpendicular to IA?
And that actually ends up
Yeah.
being IT, or sorry. Okay.
Yeah, let that point. Yeah, can you call that intersection? Like that line with with JM.
JM. Okay. Oh, they meet on the circle, I guess, right? That's what you're gonna prove?
Yeah. I have to use a fifth point to prove that HTIM cyclic. So,
Okay.
I claim that TINM is cyclic.
TIN.
So that is because of when you do an inversion with circle BIC.
Mm-hmm.
You invert about circle BIC, then you will see it immediately.
So TINM is cyclic by an inversion about BIC. Say by.
And then I'm gonna prove that I'm gonna prove that HMNI is cyclic.
HMNI is cyclic. Okay.
Yeah, and wait, let me just think about this for a second.
Okay.
Okay, so can you let L be the reflection? Oh, actually, you already have L. So can you call the reflection of I with respect to line MJ?
Okay.
Yeah, let's call it I prime. So my claim is that triangle JOI prime, it is actually JOI prime. It is similar to triangle IMH.
Okay.
So the point of constructing point I prime like this is to prove the fact that angle IMH is actually equal to angle JOI prime.
Okay.
And yeah, and those two similar triangles, you can prove it by using side angle psi.
Okay. So the ratio, you can use ratios basically.
The ratio of wait, let me see.
OJ
The
over
ratio
OI.
of IH over IM is equal to the ratio TI prime JI prime over JO.
Okay. So let I prime be the reflection of I over JM. Then JOI prime is similar to JOI prime is similar to IMH. For IMH by side angle side similarity. All right.
Okay, so we have angle JOI prime.
JOI prime
Is equal to angle IMH.
Okay.
And actually, you know what? I actually posted this proof on our Discord server like a long time ago when the session when this session happened.
Okay.
Yeah, so maybe if you scroll back all the way down there and you find it, you will see my solution.
All right.
Yeah, but the main thing is that after you have those two similar triangle, the rest is just angle chasing to prove that angle HMN is equal to angle FIN.
HMN is FIN. Okay.
FIN. Yeah, it's
Fine,
just
I'll
angle
just-
chase.
Right.
Like the main idea is just the similar triangle.
That means that HMNI is cyclic. Or sorry, HTIMN is cyclic. All right. So HMN, that's HMI plus IMN, I'm guessing is what you're thinking. So HMI is the same as JOI prime, and IMN. IMN is we know this is perpendicular, so it would be 90 minus IJM. I think that's the key. And then, well, no, it would be, okay. Yeah, I think I'd have to think about it a little bit more, but it makes sense, the idea. All right, we could take a quick look at another problem. Just the last 5 minutes. This one looks interesting. I'll just draw it up and see. So this is Indonesia. So what happened? A, B, C. E and D are on the circumcircle BIC. So the center of that's obviously the midpoint. So yeah, this might be a problem that could be solved with inversion. Inversion about the midpoint of arc BC. So AE and ID are both perpendicular to BC. Okay, so we just draw perpendiculars here. So AE and ID, so they both lie on it. Oh, this is kind of interesting. But I don't know which point E is, that's the problem. I know, so for I, it would have to be this. So this would have to be D, but I don't know which point E is. So I'll just assume it's that. M is the midpoint of BC. Whoops, let me call this N. F is the point of tangency of A. G is the intersection of DE with the circle. So, so maybe this is the real point E, I guess. So that it intersects the circle G, and then we want to show GM and NF intersect on the circle. Wait. G. Yeah. Prove that GM. That doesn't sound right. GM and NF. Let me read this one more time. So I is the in-center, E and D are, lie on gamma and the circumcircle. So E should be this point. That's my bad. So really this should be E. I was thinking too fast. And then G is this point. And then we want to show that GM and NF, interesting. Okay. But, it's the midpoint of the arc containing A. Whoops. I'm not doing so great today. So this is the real N. I think I still might be missing something because that still doesn't look true. So this is N.
Doesn't like D lie on G.
Does what?
Doesn't D like on circumcircle of ABC. D, point D.
Point D. D, it says D. So I think E lies on the circumcircle of ABC, but I think D is supposed to lie on BIC. I think that. I don't know for sure the way it's written. But we want to show GM. But yeah, here it doesn't look like GM and NF. F is the AX circle. Okay. All right, so I'm gonna have to draw a couple more things before I can understand this problem. So basically it's saying if we drew the AX circle, then if we connected it with point N, it would intersect this circle at H. All right, so we're out of time. I guess I could just draw that really quickly because it shouldn't take that long. Basically by the in-center, X-center lemma, I could just reflect this over M. And then it's saying that N, J prime, and H should be collinear. That's kind of interesting. Okay, so D and E are defined like this. We let it intersect at J. Basically, we want to show, GM and NJ prime, or we call it NF, meet at a point on this circle. It's probably not super difficult. It's probably just an angle chase or something like that, I would guess. But we are out of time. So yeah, thanks everyone for sticking around. I know we spent a long time on that one problem, but I feel like maybe it encouraged me to use inversion more. So I will start learning that and try to be more confident in applying it. And some of the problems, maybe next time I'll actually start with this problem, some of the other ones that I didn't get to. So for everyone watching on YouTube, if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So thanks again for watching and have a great day. All right, I will stop the recording.